A great day to one and all. Before we proceed with our actual lesson for today, let us have a quick review of some equations that necessitate the use of radicals. So radicals are usually discussed in the grade 9 level, but I have to review these radicals or this topic because this will be necessary for our next lesson. Let us be reminded, and please take note, given a and x to be elements of your real numbers, and if you have n here, which is a natural number, and if you have x raised to n equals a, then this implies that x is equal to the nth root of a if n is an odd number greater than 1. So to understand further what this means, let us have the following examples. Solve for x in each of the following. Letter A, x cubed equals 125. So if you could see from this one, the exponent of x is 3, and that's equal to 125. And using that certain concept in the previous slide, this actually implies that x is equal to the cube root of 125. So the exponent of x here becomes the index of the root here. And be reminded, I hope you could still remember some terms. So this thing here is called your radical sign. 3 here, this small number here, it's what you call the index of your root. And this 125, which is under your radical sign, is what you call radicand. And if you could still remember, if you could notice, 5 cubed is equal to 125. And thus, x is equal to 5. Because the cube root of 125 is 5. I hope you got it. Let's have letter B. X to the 5th equals negative 32. Applying again the same concept, it will become what? It will become x equals the 5th root of negative 32. And you have to ask yourself, what number, when taken as a factor 5 times, results to negative 32? And if your guess is negative 2, or if your answer is negative 2, you got it right. Because negative 2 quantity to the 5th is equal to negative 32. If you could check, negative 2 times negative 2, that's 4. Times negative 2, that's negative 8. Times negative 2, 16. Times negative 2, negative 32. Indeed, negative 2 is the value of x in this problem. Letter C, x cubed equals 7. So this one is pretty straightforward. So x is equal to the cube root of 7. You could notice that 7 has no other perfect cube factors except 1. Hence, this is already in simplest form and could no longer be simplified. How about letter D? X raised to 5 equals negative 1 million. For this one, of course, it will become x equals the 5th root of negative 1 million. And you might ask yourself, is negative 1 million a perfect 5th power? And the answer is no. But we know that it has a perfect 5th power factor, which is 100,000. But for now, I will express negative 1 million as negative 100,000 times 10. You could see that if you multiply negative 100,000 and 10, it will result to negative 1 million. So we just re-express it in another way, and they are in fact equal with one another. From here, remember, you might ask, sir, how come you place the negative in the 100,000 and why not on the 10? Because later on, as much as possible, in simplifying radicals, we do not want a negative value of the radicand. And since negative 100,000 is a perfect fifth power, and later on you could extract its fifth root, that's why I intend to place the negative as part of the 100,000. We know that negative 10 to the fifth is equal to negative 100,000. Hence, it's the fifth root of negative 100,000 is negative 10. And since 10 is no longer it's not a perfect fifth power, so it will stay inside. Hence, you have here the fifth root of 10. So x is equal to negative 10 times the fifth root of 10. I hope you got it. From these examples I gave you, you could see that the exponents or the indices of your roots are all odd numbers. What about if it will be an even number? So take note, if it is even, give an x element of real numbers, and n is a natural number here, and that a certain a as a positive real number, and if you have x raised to n is equal to a, this implies that x is equal to the plus minus the nth root of a, again provided that n is an even natural number. Let's have, I will explain later on how come there should be a plus minus. I think you are familiar with this. We just have to review or to, let's say, refresh some of it. So for example, if you have x squared equals 4, similarly, it will become x is equal to the square root of 4. Note that you cannot see a 2 here, but if the index of your root is not mentioned, it is understood to be 2. And since 2 is even, there should be a plus minus. And we know that 4 is a perfect square, so square root of 4 is 2. Hence, x is equal to plus minus 2. This means that x, your x sub 1, or the first value of x could be 2, and x sub 2, or the second possible value of x, is negative 2. Hence, you have two values. And you might try, if you square 2, if you square a real number, let's have this 2 first. 2 squared, you get 4. If you square negative 2, if you square a negative real number, it will also give you a positive value, right? Case in point, negative 2 quantity squared is still 4. You could see squaring a positive or a negative real number yields a positive real number. That is why there are chances that, that's why be reminded that if it is even here, if the index of the root is even, or the exponent here is even, then you have to place a plus and minus, because the square of a real number, of a positive or negative real number, is always positive. But of course, if you will square 0, it will still be 0. And 0 is neither positive nor negative. I hope you got it. Let's have letter B. X to the fourth equals 81. From here, using the previous concept, you have x is equal to the fourth root of 81. But since 4 is even here, then we have to place a plus and minus. So x is equal to plus minus the fourth root of 81. We know that 81 is a perfect fourth power. Why? It is actually 3 to the fourth, or 3 times 3 times 3 times 3. Hence, x here is plus minus 3, which tells us that x is either 3 or negative 3 for this case. Letter C. How about if you have x squared equals 12? Applying the said concept again, you have x equals plus minus square root of 12. But 12 is not a perfect square, but it has a perfect square factor, the largest of which is 4. Hence, I will copy everything and just express 12 as 4 times 3. Extracting the square root of 4, which is 2, so you have x equals plus minus 2, and the square root of 3 will be copied. Hence, your x could either be 2 square root of 3 or negative 2 square root of 3. Okay? Let's have letter D. One more. If you have x to the fourth equals 32, then it becomes, using a similar reasoning, you have x equals plus minus the fourth root of 32. But remember, 32 is not a perfect fourth power, but it has 16 as the largest perfect fourth power factor. Hence, the 32 there is expressed as 16 times 2. Fourth root of 16 is 2. And so we have here plus minus 2. But the 2 has to remain inside the fourth root symbol. So we have here x equals plus minus 2 fourth root of 2. And you have here these two values. 2 fourth root of 2 or negative 2 fourth root of 2. I hope you got this. Take note. You might ask, are these the only, for example, for letter B, is 3? I mean, are 3 and negative 3 are the only values? Not necessarily. There's a chance that some of the roots are either irrational or, let's say, imaginary. For now, let us stick with this one. And the treatment of complex or imaginary roots will be discussed next time. We stick with real roots for now. All right. So again, with that said, this brings me to our next topic, finding common ratio of geometric sequences. I need to discuss those because those things are needed for this topic. I am Mr. Kim J.C. Ensho, a faculty member of Iloilo National High School SPSTE, and I'm hoping that you will be learning something from today's lesson. Let's review. Based on the last video, I discussed with you the explicit form of a geometric sequence. That is, a sub n is equal to a sub 1 times r raised to n minus 1, where a sub n here is the nth term, a sub 1 is the first term, n is the number of terms, and r is the common ratio. And note, this is true if you have geometric sequences. Okay? Let's have these exercises. Suppose the following are terms of a geometric sequence. Find r, or the common ratio. For example, the first term is 10 and the fourth term is 80. What's the common ratio? From here, using the explicit formula again of your geometric sequence, of the nth term of your geometric sequence, you could see we have a sub 1 is 10 and a sub 4 is 80. You could see that the highest subscript here of your term is 4. So for now, let us represent our n as 4. Replacing all n's by 4 gives us a sub 4 is equal to a sub 1 times r to the 4 minus 1, or the exponent simplifies to 3. So a to the 4th is equal to a sub 1 r cubed. And you could see, what have you noticed? A sub 4 is 80 and a sub 1 is 10. By substitution, you have 80 equals 10 r cubed. We wanted to isolate the term with the r. Hence, I will be dividing both sides by 10, and that gives us 8 equals r cubed. So you see, this time you have an exponential equation, you have an equation here rather, and using the theorems earlier, you could see that the exponent of your r is odd. So hence, you have cube root of 8 equals r. There's no need to place a plus and minus here. Remember, you place only a plus or minus symbol here if you have an even index of the root, like 2, 4, 6, like square root, 4th root, 6th root, 8th root, and so on. We know that the cube root of 8 is 2. Hence, the common ratio of this particular sequence, this geometric sequence, is 2. And if you got 2, okay, I hope you got it. Let's have another one. Suppose the first term is 50 and the third term is 2. Using a similar reasoning earlier, the highest subscript here is 3. Hence, we will let n be equal to 3 and substitute all n's by 3 in this explicit form of the n term. With such, you have a cubed equals a sub 1 r to the 3 minus 1, or a sub 3 equals a sub 1 r squared. You could see from here again that the third term is 2. The first term is 50. By substitution, you have 2 equals 50 r squared. Dividing both sides by 50 to isolate the term with the variable. So 2 over 50 equals r squared. But 2 over 50 is equal to 1 over 25, right? Equals r squared. From here, we will take the square root of both sides. So, but since the index here is 2 and 2 is even, and by what we discussed earlier, there is a need to place a plus and minus sign. Hence, plus minus the square root of 1 over 25 equals r. And if you will take the square root of a certain fraction, be reminded or remember that you have to get the square root of both numerator and denominator. So the square root of 1 is 1. The square root of 25 is 5. Hence, the value of r is plus minus 1/5. And using again a similar reasoning, your common ratio could either be 1/5 or negative 1/5. And this is telling us that there are 2 possible common ratios, and this is implying that there are 2 possible geometric sequences that satisfy the given information. I hope you understood it. We will have more of these exercises later on so that you will not get confused. Letter D. In a geometric sequence, the third term is 3 and the sixth term is 192. Find the common ratio, the first term, and the eighth term. So from here, we will go beyond finding r, and we need to also to look for the other information. So for the solution, again, you see the The third term, remember the explicit formula earlier? Replacing all n's by 3, you will have a sub 3 is equal to a sub 1 times r raised to 3 minus 1 or r squared. So a sub 3 equals a sub 1 r squared, but a sub 3 is equal to 3, right? That's the reason I equated a sub 1 r squared with 3 also. For the second given, which is a sub 6, you could also see from here that what? Your n is 6, so replacing all n's by 6, you have a sub 6 equals a sub 1 r to the 6 minus 1 or r to the 5th equals its value, which is 192. And what do we do next? To look for your common ratio, you have to divide the term with the higher subscript with the one with the lower subscript. So in this case, I will divide both sides of the sixth term and the third term. I will divide their corresponding sides. So if you could see, the left sides here are a sub 1 r to the 5th divided by a sub 1 r squared. So you have it here equals the term with the higher subscript divided by the value of the term with the lower subscript, 192 over 3. So this divided by this, 192 divided by this. If you did it the other way around, it's also okay. It's just that for my case, I prefer the term with the higher subscript to be in the numerator part. That's why I have this. And we have to remember how to divide polynomials. So you could see a sub 1 divided by a sub 1 will become 1, right? It's 1. R to the 5th divided by r squared gives us r cubed. Since the exponent of the expression in the numerator is larger than that of the denominator, that is why I have just copied the common base and subtract 5 minus 2, 3. Equals 192 divided by 3 or 64. And you have r cubed equals 64. Taking the cube root of both sides again, this gives us the value of your common ratio, which is 4. So you have only one value of the common ratio, which is 4. And if there's only one value of r, this is in fact telling you that there is only one, most likely only one geometric sequence with real terms. And if you got 4, great job. Now, we got r, we still need a sub 1, right? To get the value of a sub 1, we could substitute it to either, we could substitute the value of r either to a sub 1 r squared equals 3 or to a sub 1 r to the 5th equals 192. Substituting it to any of these two equations will still give you the same correct answer. Since r is 4, and I chose to have the third equation, by the way, the a sub 3 rather, which is a sub 1 r squared equals 3. Replacing r by 4 gives you a sub 1 times 4 squared equals 3. 4 squared is 16, so a sub 1 times 16 equals 3. And dividing both sides by 16 gives us the first term as 3 over 16. And now, since we have the value of the first term and the common ratio, it is now possible to get the value of your 8th term. That is why substituting it to its explicit form, which is a sub n equals a sub 1 r to the n minus 1, replacing all n's by 8, because your subscript here is 8, and by substitution of your a sub 1 and common ratio, you get a sub 8 equals 3/16 times 4 raised to 8 minus 1. Be reminded again that the exponent here is that of your r, which is 4, not of 3 over 16. So I expressed 3 over 16 as 3 over 16. I made it 4 squared because anyway, same base here. This is 4 raised to 7. And using your laws of exponents, be reminded that if you have 4 raised to 7 divided by 4 squared, that is 4 to the 5th power. And 3 times 4 to the 5th, using your calculators, 4 to the 5th, by the way, is 4 times 4 times 4 times 4 times 4, or 1024. And the 8th term indeed is 3072. If you got 3072, great job. And before we proceed with some more problems, be reminded that feel free to pause the video from time to time and check, do the problems on your own and see if you get the correct answer. Let's have another one. In a geometric sequence, a sub 3 equals 72 and a sub 5 equals 648. Give all possible geometric sequence or sequences and determine the value of the 8th term. Feel free to pause the video, but right now, I will reveal the solution. Using again this explicit form for a sub 3, I will let n be equal to 3. And by substitution here, that's a sub 3 equals a sub 1 times r squared, which is equal to 72. For the second given, a sub 5 equals 648, we will let n equals 5. By substitution again, that's a sub 5 equals a sub 1 r to the 4th equals the value of the 5th term, which is 648. And the subscript of a sub 5 is larger than that of a sub 3. So for my case, I will divide a sub 5 by a sub 3. So that's a sub 1 r to the 4th divided by a sub 1 r squared on the left-hand side. And that is equal to 648 over 72 on the right-hand side. The left-hand side simplifies to r squared. How come? A sub 1 divided by a sub 1 is 1. R to the 4th divided by r squared, it's r squared because 4 minus 2 is 2. So, and the exponent of the numerator is greater than that of the denominator. And 648 all over 72 or divided by 72 is 9. So r squared equals 9. And you see, we will get the square root of both sides to solve for r. But since our index of the root, which is 2, is even, there should be a plus minus sign before the square root of 9. Square root of 9 is 3. Hence, r, your common ratio is either 3 or negative 3. And what does a common ratio of 3 or negative 3 tell you? This is giving us two possible common ratios. And remember this, if you have two possible common ratios, then there are also two possible geometric sequences with real common ratios and with real values, for example, with real values of the terms for this case. Now, so since we have two cases, let's take the first case when your R or your common ratio is positive 3. If that's the case, I will substitute it to the to this one earlier, which is a sub 1 r squared equals 72. Replacing r with 3 gives a sub 1 times 3 squared equals 72. 3 squared is 9. So 9a sub 1 equals 72. Dividing both sides by 9 gives a sub 1 equals 8. So the first term here is 8. And since your r is 3 and your first term is 8, we can now determine the value of the 8th term using the explicit formula. But for now, let's give all possible geometric sequences. So the first term is 8. And since your common ratio is 3, so we have to multiply by 3 all throughout. 8 times 3, 24. Times 3, 72. Times 3, 216. Times 3, 648. Times 3, 1,944, and so on. You could see from this case that the third term is indeed 72, and the fifth term is indeed 648. So therefore, this r equals 3 and a sub 1 equals 8 is true and valid for this particular problem, and they both satisfy the given conditions. So looking for the eighth term now of this sequence and substituting here the n by 8 and the rest of a sub 1 and r. A sub 8 is equal to 8 times 3 raised to 8 minus 1. 3, this becomes 3 raised to 7, or 2,187. Please verify that with your calculator if you wish. And 8 times 2,187 gives the eighth term as 17,496. Okay, I hope you got it. But that's the first case. If your r is negative 3, it's positive 3 rather. How about if we get the second case, that your r is negative 3? By substitution again to a sub 1 r squared equals 72. Take note, you are free to substitute it either to a sub 3 or to a sub 5 earlier. I chose a sub 3 because for me, I find it easier to work with equations with smaller numbers. Now, since r is negative 3, so you have a sub 1 equals negative 3, quantity squared equals 72. You square negative 3, it will give you 9, right? So still 9a sub 1 equals 72. Dividing both sides by 9, you get the first term as 8. And if you could see or if you could have noticed, either in case 1 or in case 2, for this case only, you notice that the first term is 8, regardless if r is positive or negative. So given your common ratio of negative 3 and a sub 1 equals 8, a possible geometric sequence is, so let's have 8 first here as the first term. Times negative 3 will give you negative 24. Negative 24 times negative 3 gives 72. Sir, how come positive? Because negative times negative is positive. 72 times negative 3 is negative 216. Negative 216 times negative 3 is 648. 648 times negative 3 is negative 1,944, and so on. And if you could see again, the third term is indeed 72, and the fifth term is indeed 648. So in either case, whether your r is positive or negative, you see that they both satisfy the given conditions that the third and fifth terms are 72 and 648 respectively. But we are not yet done. We still need to look for the value of the eighth term. Using again the formula, a sub 8 equals 8 times negative 3 raised to 8 minus 1. Negative 3 raised to 8 minus 1, the exponent simplifies to 7. Negative 3 raised to 7 will give you negative 2,187. Remember, a negative real number raised to an odd natural number will give you a negative value. That's why a sub 8 is 8 times negative 2,187, or negative 17,000 496. Earlier in case 1, the common ratio was positive 17,496, but for this second case, it's negative. That's why be very careful. There are instances that your first term might be the same. They might be different depending on the given or the condition. The indicated term might also be the same or might be different. Or if that's the case, there might be instances wherein the common ratios may have opposite signs. That's why be very careful. Make sure that you solve correctly, follow the correct algebra, and I believe that you could get the answers with no problem. All right, so far so good. But if you could notice for this particular case, you have 8. For the first case, you have 8, 24, 72, 216, 648, 1944, and so on. For the second case, you have 8, negative 24, 72, negative 216, and so on. And you also have 648, negative 1944. Okay. You could see some terms were in red and the rest were in black, and they are alternating, right? That's why, remember, for case 1, since the common ratio is positive, that's why all terms have the same sign. Remember, if your common ratio is positive, then all terms are all positive or all negative, depending on the sign of your first term. However, if your common ratio is negative, expect that the signs will be alternating, just like this. If you could see, the first, third, fifth terms are the same, but the second, fourth, and sixth terms have different signs. And with that case, you could actually write them into one sequence, that is 8 plus this, what you see, 8 here, just the same sign, so it's positive 8 only, or simply 8. The second terms, one could be positive or negative. That's why I place here plus minus 24. The third term, same, so 72. For the fourth term, plus minus negative 216. The fifth term, 648. For the sixth term, plus minus 1944, and so on. If you will write your final answers in this way, that's correct. But if you write them into a single expression like this, it is also correct. Okay? So choose either this method or this one. They are both correct. I hope you got it. And with that, I give you this independent set, which should be written on a piece of paper, or you could also do this in your notebook. Please have this done and pass it via private message to my account on or before October 7, 2022, Friday. So here are these, I just give you these 1 and 2, and each has A and B. And I hope that you learned something out of this lesson today, and I wish you all the best in doing your independent set. With that, thank you very much, and a great day to one and all.